The solar system has boundaries we've mapped for centuries, edges we thought we understood. But recent discoveries from NASA's deep space monitoring networks have revealed something unsettling lurking in the farthest reaches of our cosmic neighborhood. Multiple detection systems, spacecraft, ground-based observatories, and space telescopes have identified anomalous structures and objects in regions where our models predicted near-emptiness. These aren't distant galaxies or background stars. They're within our solar system's gravitational influence, moving in ways that challenge our understanding of orbital mechanics and planetary formation. What NASA has found near the edge of the solar system isn't just scientifically puzzling, it's forcing astronomers to reconsider fundamental assumptions about how solar systems evolve, what lies beyond Neptune's orbit, and whether we've been measuring the true extent of the Sun's domain correctly. The data streaming back from the outer solar system suggests we're missing massive components of our own cosmic backyard, hidden in darkness for billions of years. The heliopause boundary and its unexpected thickness. The heliopause represents the boundary where the solar wind, a continuous stream of charged particles emanating from the Sun, meets the interstellar medium. For decades, scientists modeled this boundary as a relatively sharp transition zone, a cosmic shoreline where our Sun's influence abruptly ends and interstellar space begins. NASA's Voyager 1 crossed this boundary in 2012, approximately 121 astronomical units from the Sun, followed by Voyager 2 inches 2018 at roughly 119 astronomical units. But the data they transmitted back revealed something unexpected. The heliopause isn't a clean dividing line, but a turbulent, dynamic region far thicker and more complex than theoretical models predicted. The Voyager spacecraft detected multiple crossings of the boundary, indicating the heliopause oscillates and ripples like a flag in wind. Rather than a single transition lasting hours or days, the probes measured fluctuations extending across billions of kilometers. The plasma wave instrument on Voyager 1 recorded density variations suggesting the boundary zone spans at least 5 to 7 astronomical units in thickness, 10 times wider than expected. This discovery indicates the solar wind doesn't simply stop when it encounters interstellar space. Instead, it creates a massive turbulent mixing zone where solar and interstellar particles interact in ways not accounted for in previous models. The temperature profile across the heliopause boundary presents another puzzle. Scientists expected temperatures to drop sharply as the probes exited the heliosphere, but instead, Voyager measurements showed temperature increases in certain particle populations. Electrons in the interstellar medium just beyond the heliopause reached temperatures exceeding 30,000 Kelvin, far hotter than the cooler solar wind plasma just inside. This temperature inversion suggests unknown heating mechanisms operating at the solar system's edge, possibly magnetic reconnection events, where magnetic field lines from the Sun and interstellar space break and reconnect, releasing enormous amounts of energy. The heliopause boundary's shape also defies simple models. Rather than a symmetric bubble around the Sun, data from the Interstellar Boundary Explorer, IBEX, mission revealed asymmetries and structures resembling a croissant or kidney bean. The side of the heliosphere facing the direction of the Sun's motion through the galaxy appears compressed, while the trailing edge stretches into a long tail called the heliotail, extending possibly hundreds of astronomical units behind us. Recent computer simulations incorporating Voyager and IBEX data suggest this tail may be unstable, breaking apart and reforming in ways that could affect how cosmic rays penetrate the inner solar system. The discovery of a hydrogen wall just beyond the heliopause adds another layer of complexity. IBEX instruments detected a distinct accumulation of neutral hydrogen atoms piling up where the solar wind slows and compresses against interstellar material. This wall scatters ultraviolet light from distant stars, creating a faint glow detectable by specialized instruments. The wall's density and distribution provide clues about the composition and velocity of the interstellar medium surrounding our solar system, revealing that we're moving through a region of space slightly denser and warmer than average, possibly the edge of a local interstellar cloud formed by ancient supernova explosions. Magnetic field measurements near the heliopause revealed yet another surprise. The interstellar magnetic field strength exceeds predictions by a factor of 2 to 3. The Voyager spacecraft measured interstellar magnetic field strengths around 5 to 6 nanoteslas, significantly stronger than the 1 to 2 nanotesla values expected from earlier indirect measurements. This stronger field affects how cosmic rays' high-energy particles from outside the solar system enter the heliosphere and reach Earth. Understanding these magnetic interactions becomes crucial for protecting future deep space missions, and even for comprehending how galactic cosmic rays influence Earth's atmosphere and climate over geological timescales. The plasma density in the region just beyond the heliopause measures approximately 0.8 particles per cubic centimetre, sparse by terrestrial standards, but about 40 times denser than the solar wind plasma in the outer heliosphere. This density difference drives complex fluid dynamics at the boundary, creating shock waves, instabilities, and turbulent mixing that no spacecraft has yet fully characterized. NASA scientists now recognize that the heliopause represents not an edge but a transition zone, a frontier region where our solar system doesn't end cleanly but gradually merges with the galaxy beyond. The Kuiper belt's hidden mass concentrations. Beyond Neptune's orbit lies the Kuiper belt, a vast region of icy bodies extending from roughly 30 to 50 astronomical units from the Sunday. For years, astronomers catalogued thousands of these objects, remnants from the solar system's formation, assuming they understood the belt's mass distribution. But precise tracking of spacecraft trajectories, combined with surveys from ground-based telescopes and the Hubble Space Telescope, revealed gravitational anomalies, suggesting substantial mass concentrations in regions where few objects have been directly observed. These hidden concentrations worry scientists because they indicate our census of the outer solar system remains woefully incomplete. The first hints emerge from the orbits of known Kuiper belt objects themselves. Detailed orbital calculations for several hundred trans-Neptunian objects revealed subtle perturbations, tiny deviations from paths calculated using only the known planet's gravity. These perturbations suggested additional mass somewhere in the outer solar system, pulling on these distant bodies with detectable but small gravitational forces. Computer models attempting to reproduce the observed orbital distribution required, adding unseen mass equivalent to several Earth masses distributed through specific regions of the Kuiper belt. Observations from the Dark Energy Survey and the Pan-STARRS project identified clustering patterns in Kuiper belt object orbits that shouldn't exist if the belt contained only the catalogued bodies. Multiple objects share similar orbital inclinations and longitudes of ascending nodes, statistical coincidences too unlikely to arise by chance. These clustering patterns point toward gravitational shepherding by unseen massive objects, bodies large enough to gravitationally organize their neighbors, but too faint or distant to have been detected yet. Estimates suggest these hidden shepherds could range from Mars size to potentially larger than Earth, lurking in the Kuiper belt's outer reaches. The orbital velocity measurements of New Horizons spacecraft as it traversed the Kuiper belt provided additional evidence. Radio tracking of the spacecraft's position with accuracy better than 1 kilometer revealed tiny velocity changes inconsistent with the gravity of known objects alone. Though small, just fractions of a millimeter per second, these velocity perturbations accumulated over the spacecraft's journey, suggesting it passed through regions of slightly enhanced gravitational pull. Mapping these subtle gravitational variations creates a density map of the Kuiper belt, revealing lumps and concentrations invisible to direct observation. Infrared surveys from the Wide Field Infrared Survey Explorer (WISE) mission placed important constraints on what these hidden masses could be. WISE scanned the entire sky in infrared wavelengths, sensitive to the faint heat emission from objects warmer than the cosmic background. The survey detected no massive planets in the inner Kuiper belt, ruling out anything larger than Neptune within 50 astronomical units. But WISE's sensitivity dropped for more distant or colder objects, leaving open the possibility of substantial mass in the belt's outer edge, or in darker, colder bodies made primarily of rock rather than ice. The size distribution of detected Kuiper belt objects presents another puzzle. Surveys find many small objects tens to hundreds of kilometers across, and a handful of large ones like Pluto, Eris, Makemake, and Haumea. But there's a suspicious gap. Fewer medium-sized objects than expected. Collisional evolution models predict a smooth distribution across all sizes, but observations show a deficit of objects in the 100 to 500 kilometer range. This divot in the size distribution could result from hidden massive bodies that gravitationally scattered medium-sized objects into the inner solar system billions of years ago, preferentially removing that size class while leaving smaller debris and larger survivors. Dynamical simulations of Kuiper belt evolution reveal that the current mass, estimated at roughly 1/10 Earth's mass in all detected objects, seems insufficient to have produced the observed population structure. The belt appears depleted, containing perhaps 1% of the mass that should have formed in that region based on the solar nebula's initial density. Where did the missing 99% go? Some were ejected by Neptune during its outward migration, some fell into the Sun, but a significant fraction may still lurk in the belt's outermost regions, dark, cold, and nearly invisible from Earth. These undiscovered reservoirs of primordial material could contain crucial information about the solar system's birth while presenting navigation hazards for future deep space missions. Extreme trans-Neptunian objects and orbital anomalies. Far beyond the classical Kuiper belt, in the frigid darkness beyond 50 astronomical units, astronomers have identified a population of extreme trans-Neptunian objects with orbits so eccentric and distant they spend most of their time in the solar system's remote frontier. Objects like Sedna 2012, VP 113, and the recently discovered Lilikuhonua trace enormous elliptical paths, carrying them hundreds of astronomical units from the Sunday. But their orbits exhibit peculiar clustering patterns and orientations that gravitational interactions with known planets cannot explain. These anomalies have worried scientists because they point toward either an undiscovered massive planet in the outer solar system or a more exotic alternative. A close encounter with a passing star that scrambled the solar system's distant architecture. Sedna, discovered in 2003, follows one of the most unusual orbits known. Its closest approach to the Sun perihelion lies at 76 astronomical units, well beyond Neptune's influence. Its aphelion, the farthest point, reaches approximately 936 astronomical units, taking roughly 11,000 years to complete one orbit. Sedna never comes close enough to Neptune for that planet's gravity to have shaped its path, yet something placed it in this distant, detached orbit. No known process in standard solar system formation models produces such orbits naturally. Either Sedna formed elsewhere and was captured, or some massive perturber sculpted its orbit billions of years ago. The discovery of additional extreme objects strengthened the mystery. 2012, VP 113, nicknamed Biden, after the vice president at the time of its discovery, has a perihelion of 80 astronomical units, even more detached than Sedna. Multiple objects with perihelia beyond 50 astronomical units now populate the catalogue, each requiring an explanation for how they arrived in such remote orbits. Statistical analysis of these orbits revealed they're not randomly oriented. Their perihelia cluster in similar directions, and their orbital planes show modest alignment. With only a dozen such objects known, the clustering could be coincidence, but probability calculations suggest only a few % chance of such alignment arising randomly. This clustering led to the Planet 9 hypothesis, the proposal that an unseen planet, 5 to 10 times Earth's mass, orbits the Sun at distances of 400 to 800 astronomical units. Computer simulations show that such a planet, on an appropriately inclined and eccentric orbit, could gravitationally shepherd extreme trans-Neptunian objects into the observed clustering patterns over millions of years. The planet would also explain other oddities: objects with orbits perpendicular to the planetary plane, retrograde objects orbiting backward, and the overall depletion of the Kuiper belt's outer edge. Multiple research groups have refined the Planet 9 hypothesis, narrowing its predicted location and properties, but despite extensive searches, no telescope has yet found it. Alternative explanations exist. Some astronomers propose that the clustering results from observational bias. Our telescopes search certain regions of sky preferentially, creating apparent clustering that doesn't reflect the true distribution. Others suggest the early solar system passed through a dense portion of the galaxy's star-forming region, and gravitational perturbations from nearby young stars sculpted these distant orbits. More exotic proposals invoke a primordial black hole of several Earth masses, captured by the Sun's gravity and now orbiting in the outer solar system, invisible but gravitationally influential. Each hypothesis makes testable predictions, but confirming or ruling them out requires surveying larger swaths of sky to find more extreme trans-Neptunian objects and better characterize their orbital distribution. The discovery of objects like 2018 VG18, nicknamed Far Out, at 120 astronomical units, and later 2018 AG37, nicknamed Far Out, with a perihelion of 27 astronomical units, but an aphelion exceeding 175 astronomical units, demonstrates that the solar system's distant reaches remain largely unexplored. Each new discovery refines our understanding of this mysterious population. Recent surveys suggest extreme trans-Neptunian objects may be more common than previously thought, with predictions of hundreds or thousands awaiting detection. Their orbital properties encode the solar system's early history, a record of planetary migration, stellar encounters, and gravitational interactions spanning billions of years. The velocity dispersion of extreme trans-Neptunian objects provides additional constraints. If these objects formed in place, they should move slowly relative to each other, their velocities reflecting gentle gravitational interactions over time. But if they formed closer to the Sun and were scattered outward, they'd retain higher velocities. Measurements of mutual velocities suggest a mixed population. Some appear scattered, while others seem to have formed in situ. This diversity implies multiple formation pathways operated, possibly including capture of objects from other stars during the Sun's birth in a star cluster, gravitational scattering by a now-ejected ice giant planet, and in-place formation from the outer edges of the protoplanetary disk. The Oort cloud's inner edge and unexpected cometary activity. The Oort cloud represents the solar system's most distant reservoir of comets, a vast spherical shell of icy bodies extending from roughly 2,000 to 100,000 astronomical units from the Sunday. While no Oort cloud object has ever been directly observed in its distant orbit, astronomers infer its existence from long-period comets that occasionally plunge into the inner solar system from random directions. But recent observations of cometary activity, originating from unexpectedly close distances between 100 and 2,000 astronomical units, suggest the Oort cloud's inner edge contains more active objects than theoretical models predict. This unexpected cometary activity worries scientists because it implies either our understanding of cometary activation mechanisms is incomplete, or the inner Oort cloud's population differs significantly from assumptions. Traditional models describe the Oort cloud as dormant, a deep freeze where comets remain inactive for billions of years until a passing star's gravity nudges them toward the Sunday. But observations from surveys like Pan-STARRS and the Catalina Sky Survey detected comets brightening at distances exceeding 10 astronomical units, far beyond where solar heating should sublimate significant ice. These distant activation events suggest mechanisms other than solar heating, perhaps radioactive decay in comet interiors, crystallization of amorphous ice releasing stored energy, or even exotic processes like partial sublimation of supervolatile ices, such as carbon monoxide or nitrogen, that remain frozen closer to the Sun but begin outgassing at extreme distances. The discovery of Comet C, 2017K, 2 Pan-STARRS, provided a striking example. This comet showed clear cometary activity, a visible coma of gas and dust when first detected beyond Saturn's orbit, at approximately 24 astronomical units from the Sunday. As telescopes tracked it inward, the coma persisted and even intensified, suggesting continuous activity driven by sublimating supervolatile ices. Spectroscopic observations confirmed carbon monoxide and nitrogen emissions, materials that begin sublimating at much lower temperatures than water ice. The comet's large nucleus, estimated at tens of kilometers across, and its activity at such distances indicate it originated from the Oort cloud's inner regions, where temperatures remain cold enough to preserve these volatile ices over billions of years. Statistical analysis of long-period comet orbits revealed another puzzle. These comets arrive from all directions with orbital inclinations spanning the full range from prograde to retrograde, confirming they originate from a spherical reservoir surrounding the Sunday. But the distribution of perihelion distances, how close comets pass to the Sun at their nearest point, shows unexpected features. More comets have perihelia between 2 and 4 astronomical units than models predict, while fewer graze extremely close to the Sun than expected. This anomaly suggests either observational biases favour detecting comets at intermediate distances, or physical processes preferentially destroy comets on extreme approaches. The size distribution of Oort cloud comets inferred from observations of returning long-period comets shows a deficit of small objects. Surveys detect many large comets' nuclei, several kilometers across, but fewer sub-kilometer objects than extrapolation from larger sizes predicts. This deficit could result from observational limitations. Small comets are simply too faint to detect at the distances they become active. Alternatively, collisional grinding in the Oort cloud's inner regions might have destroyed small comets over billions of years, preferentially removing them from the population. Understanding this size distribution matters for assessing impact risks and for comprehending how planetesimals formed and evolved in the early solar system. Measurements of Oort cloud comet compositions reveal surprising diversity. Some comets show compositions closely matching solar abundances of volatile elements, while others exhibit significant depletions or enhancements. This chemical diversity suggests the Oort cloud formed from material originating at different distances in the protoplanetary disk. Comets born near Jupiter differ compositionally from those formed near Uranus or Neptune, and when planetary migration scattered these objects into the Oort cloud, they mixed into a chemically heterogeneous population. Each returning comet thus carries compositional fingerprints, revealing its birthplace in the early solar system. The total mass of the Oort cloud remains highly uncertain. Estimates range from several Earth masses to hundreds of Earth masses, depending on assumptions about the size, distribution, and density of objects. Recent dynamical simulations suggest the cloud may contain more mass than previously thought, possibly exceeding 50 Earth masses. This mass represents material lost from the planetary formation zone, ejected by gravitational interactions with the giant planets. If accurate, these higher mass estimates imply the protoplanetary disk extended much farther and contained more mass than minimal mass solar nebula models predict. Interstellar medium intrusions and anomalous neutral particles. The space between the stars isn't empty but filled with the interstellar medium, a diffuse mixture of gas, dust, and cosmic rays. As the solar system moves through the galaxy at roughly 25 kilometers per second, it plows through this material like a ship through water. NASA's Interstellar Boundary Explorer, IBEX, and Voyager spacecraft have detected anomalous concentrations of neutral particles entering the heliosphere from specific directions patterns that don't match the expected uniform flow of interstellar material. These intrusions worry scientists because they suggest the local interstellar environment contains structures and variations not predicted by models, potentially affecting cosmic ray fluxes that reach Earth and influencing space weather throughout the solar system. IBEX instruments measure energetic neutral atoms, particles that form when ions in the solar wind or interstellar medium capture electrons, becoming neutral and thus able to travel in straight lines unaffected by magnetic fields. By mapping these particles' arrival directions and energies, IBEX creates images of the interaction between the solar wind and interstellar medium. Early IBEX results revealed a bright ribbon of enhanced neutral atom emission stretching across the sky, oriented perpendicular to the local interstellar magnetic field direction. This ribbon's origin remains debated, but it clearly indicates structure in the interstellar medium immediately surrounding the heliosphere. The Voyager spacecraft, having exited the heliosphere, now sample interstellar material directly. Their plasma instruments measure particle densities, velocities, and temperatures, providing ground truth for comparison with IBEX remote observations. Voyager 1's measurements revealed the interstellar medium's velocity relative to the Sun differs slightly from expectations based on observations of nearby stars. The interstellar flow appears to arrive from approximately 5 degrees different direction than predicted and moves about 3 kilometers per second slower. These discrepancies suggest the local interstellar cloud surrounding our solar system has internal structure velocity gradients and density variations that affect how material flows past the heliosphere. Analysis of interstellar helium atoms penetrating the heliosphere provides additional clues. These neutral helium atoms flow through the solar system relatively unaffected by the solar wind's magnetic field, reaching Earth's orbit and beyond. IBEX measurements of their flow direction, speed, and temperature revealed temporal variations, year-to-year changes in the interstellar helium flow properties. Such variations shouldn't occur if the interstellar medium were uniform and static. Instead, they suggest we're moving through structured interstellar material, perhaps crossing between regions with different densities, temperatures, or velocities on timescales of years to decades. Interstellar dust grains detected by instruments on spacecraft like Ulysses, Galileo, and Cassini provide another window into the local interstellar medium's composition. These dust particles, typically fractions of a micrometer in diameter, enter the solar system from the direction of interstellar flow. Analysis of their impact trajectories and, in some cases, compositional analysis of captured grains revealed the dust composition matches neither solar system material nor the average interstellar medium. The grains contain unusual silicate minerals and organic compounds, suggesting they formed in supernova ejecta or stellar winds from multiple sources, mixed in the interstellar medium over millions of years. The discovery of interstellar neutral hydrogen accumulating just beyond the heliopause, the hydrogen wall detected by IBEX, demonstrates how the solar system's motion through the galaxy affects our immediate environment. As the solar wind pushes outward, it slows and compresses when meeting interstellar material, creating a shock wave where neutral hydrogen atoms pile up. This accumulation scatters ultraviolet light from distant stars, creating a faint glow that marks the heliosphere's boundary. Variations in the hydrogen wall's thickness and density reveal details about the interstellar medium's density and the solar wind's strength over recent decades. Anomalies in cosmic ray fluxes measured by multiple spacecraft correlate with changes in the solar system's interstellar environment. Cosmic rays, high-energy particles accelerated by supernovae and other violent astrophysical processes diffuse through the galaxy and modulate as they pass through the heliosphere. The solar wind and heliospheric magnetic field partially shield the inner solar system from these particles, but the shielding effectiveness depends on solar activity and the interstellar medium's properties. Recent variations in cosmic ray intensities at Earth don't correlate perfectly with solar activity alone, suggesting changes in how efficiently the heliopause filters cosmic rays, possibly driven by variations in interstellar pressure or magnetic field strength. Magnetic field reversals at the solar system's edge. The Sun's magnetic field extends throughout the solar system, carried by the solar wind into a vast bubble called the heliosphere. But at the heliopause boundary, this solar magnetic field encounters the interstellar magnetic field threading through the galaxy. Measurements from Voyager 1 and Voyager 2, as they crossed this boundary, revealed unexpected magnetic field behavior. Rather than a clean transition from solar to interstellar fields, the spacecraft detected multiple reversals, regions where field lines twisted and sectors where magnetic field strengths fluctuated wildly. These magnetic field reversals worry scientists because they indicate instabilities at the heliopause that could affect cosmic ray entry and create space weather events throughout the solar system. Voyager 1's magnetometer recorded the first crossing of the heliopause in 2012, when magnetic field orientations abruptly changed. Inside the heliosphere, the field showed patterns consistent with solar origin field lines, spiraling outward from the Sun, reversing polarity every 11 years with the solar cycle. Beyond the heliopause, the field should align with the interstellar magnetic field, oriented roughly perpendicular to the heliosphere's motion through the galaxy. But Voyager's measurements showed something unexpected. The field direction just beyond the heliopause aligned almost parallel to the solar field for the first several months. Only gradually did it rotate toward the expected interstellar direction, taking nearly a year to complete the transition. This slow rotation suggested Voyager 1 crossed into a magnetic reconnection layer, a region where solar and interstellar magnetic field lines break, reconnect, and merge in a complex dance. Magnetic reconnection releases enormous energy, accelerating particles to high speeds and creating turbulence. The layer's thickness, several astronomical units based on how long Voyager took to traverse it, far exceeded theoretical predictions. Models suggested reconnection should occur in thin sheets, maybe tens of thousands of kilometers thick, but observations indicated a much broader transition zone. Voyager 2's heliopause crossing in 2018 provided a second data point at a different location. Its magnetometer showed a different pattern, an even more complex transition with multiple field direction changes over weeks. The field strength dropped, then increased, then dropped again, before stabilizing at interstellar values. These fluctuations indicated Voyager 2 encountered a more turbulent section of the boundary, perhaps where the heliopause itself was rippling or oscillating in response to variations in solar wind pressure or interstellar medium density. Comparing the two Voyager crossings revealed large-scale structure in the heliopause's magnetic properties. The spacecraft crossed at different locations. Voyager 1 inch the direction the Sun moves through the galaxy, the nose of the heliosphere, and Voyager 2 to one side. The different crossing experiences suggest the heliopause's magnetic structure varies with position, thicker and more turbulent on the sides than directly in front. This asymmetry likely results from the interstellar magnetic field's orientation relative to the Sun's motion, creating a draping effect where field lines pile up and compress on certain sides. Magnetic field measurements also revealed unexpected particle acceleration at the heliopause. Both Voyager spacecraft detected bursts of high-energy electrons and ions, coinciding with magnetic field changes. These energetic particles, accelerated to near-relativistic speeds, provide direct evidence that magnetic reconnection at the heliopause converts magnetic energy into particle kinetic energy. The process operates continuously, creating a source of energetic particles distinct from both solar energetic particle events and galactic cosmic rays. Understanding this acceleration mechanism matters for predicting radiation environments for future interstellar missions. The Voyagers also detected magnetic field oscillations, waves propagating along the heliopause boundary. These waves, with periods ranging from days to weeks, result from the boundary itself vibrating in response to solar wind pressure changes. When the solar wind strengthens during solar maximum, it pushes the heliopause outward. When the wind weakens during solar minimum, interstellar pressure pushes the boundary inward. These expansions and contractions propagate as waves around the heliosphere, creating a dynamic, fluctuating boundary rather than a static shell. Theoretical models now incorporate these observations to predict heliopause behavior under different conditions. Simulations show that the interstellar magnetic field strength and orientation critically affect boundary structure. Stronger fields create thicker transition zones with more intense reconnection. Tilted fields generate asymmetries, making one side of the heliosphere more magnetically complex than another. The models also predict that rare events like interstellar shock waves from nearby supernova remnants passing through the solar system could temporarily compress or even collapse the heliopause, briefly exposing the inner solar system to full interstellar conditions. Unexplained radiation belts beyond Jupiter. Unexplained radiation belts beyond Jupiter. Radiation belts, regions where high-energy charged particles trapped by magnetic fields spiral back and forth between magnetic poles, exist around all solar system planets with significant magnetic fields. Earth's Van Allen belts, Jupiter's intense radiation zones, and Saturn's more modest belts have been studied for decades. But observations from NASA's Juno spacecraft at Jupiter and data from the Voyager and Pioneer missions revealed unexpected radiation belt structures extending far beyond the giant planets into regions where magnetic fields should be, too weak to trap particles effectively. These unexplained radiation belts worry scientists because they indicate particle acceleration and trapping mechanisms not included in current models, with implications for spacecraft safety and understanding magnetospheric physics. Jupiter possesses the solar system's strongest planetary magnetic field and most intense radiation environment. Charged particles accelerated in its magnetosphere reach energies comparable to cosmic rays, creating lethal radiation zones that can damage spacecraft electronics within hours. Juno's instruments, designed with heavy radiation shielding, measured radiation belt properties with unprecedented precision during its close approaches to Jupiter. The data revealed belt structures persisting at distances exceeding 100 Jupiter radii, more than 7 million kilometers from the planet. At such distances, Jupiter's magnetic field strength drops to levels comparable to the interplanetary magnetic field, yet particles remain trapped and energized. The explanation likely involves magnetic field line distortions created by Jupiter's rapid rotation and the electromagnetic coupling between Jupiter and its moon Io. Io orbits within Jupiter's intense magnetic field, and volcanic emissions add roughly 1 ton of material per second to the magnetosphere, mostly sulfur and oxygen ions. These ions become ionized, trapped, and accelerated by Jupiter's rotating magnetic field, creating a vast torus of plasma surrounding the planet. This plasma conducts electricity, generating currents that couple back to Jupiter's ionosphere, creating aurora and energizing particles to high energies. Some of these particles escape along stretched magnetic field lines, populating radiation belts at great distances. Similar but weaker radiation belts exist at Saturn, extending beyond the ring system into the magnetosphere's outer regions. Cassini spacecraft measurements revealed these belts contain particles accelerated locally by magnetic field fluctuations rather than transported from closer to Saturn. The particle energy spectrum differs from Jupiter's radiation belts, suggesting different acceleration mechanisms. Saturn's magnetosphere rotates with the planet but also experiences significant influence from the solar wind, which periodically compresses the magnetosphere and triggers particle acceleration events. These dynamic interactions create episodic radiation enhancements rather than steady trapped populations. Voyager spacecraft detected unexpected energetic particle populations at Uranus and Neptune, despite their relatively weak magnetic fields. These ice giants possess tilted and offset magnetic fields. Uranus's field tilts 59 degrees from its rotation axis, while Neptune's tilts 47 degrees. Such complex geometries shouldn't efficiently trap particles, yet Voyager instruments measured enhanced particle fluxes in specific regions. The particles appeared recently accelerated, suggesting ongoing processes actively energize them despite the unfavorable magnetic configurations. Interplanetary space itself contains diffuse energetic particle populations that occasionally organize into belt-like structures. Observations from spacecraft like ACE and Stereo detected particle flux enhancements lasting days to weeks, localized in narrow bands of heliocentric distance or magnetic longitude. These transient radiation belts form when interplanetary shock waves, driven by fast solar wind streams or coronal mass ejections, trap and accelerate particles from the ambient solar wind. The trapped populations gradually disperse as they diffuse across magnetic field lines, but while present, they create elevated radiation environments affecting spacecraft throughout the inner solar system. The discovery of ultra-relativistic electrons in Earth's radiation belt's particles, accelerated to 99% the speed of light, or higher, demonstrated that even relatively weak magnetic fields can trap and energize particles to extreme energies under the right conditions. These particles appear during geomagnetic storms, created by very low-frequency electromagnetic waves that resonate with particle motion, progressively accelerating electrons to higher and higher energies over hours to days. Similar mechanisms likely operate at other planets, and potentially in interplanetary space, creating energetic particle populations wherever magnetic fields and plasma waves coexist. Dark comets and low albedo objects in the outer solar system. Comets traditionally appear bright because ice sublimating from their surfaces creates dusty comas that scatter sunlight efficiently. But recent surveys discovered dark comets, objects following comet-like orbits but showing little to no visible activity. Additionally, spectroscopic observations revealed numerous Kuiper belt objects with surprisingly low albedos, reflecting less than 5% of incident sunlight. These dark comets and low albedo objects worry scientists because their darkness makes them difficult to detect and track, and their compositions suggest processing by radiation or impacts that standard models of outer solar system evolution don't fully explain. The first dark comets were identified when astronomers noticed objects on highly elliptical, comet-like orbits that showed no comae or tails, even when passing close to the Sunday. Spectroscopic follow-up revealed surfaces covered in dark, carbon-rich material resembling tar or soot rather than bright ice. These objects likely began as typical comets, but after numerous passages near the Sun, their surface ice sublimated away, leaving behind a lag deposit, a dark, insulating layer of dust and organic compounds that prevents further ice sublimation even when heated. The result appears asteroid-like despite originating from the comet population. Subsequent discoveries revealed dark comets exist in the outer solar system too, objects at Kuiper belt distances with albedos below 3%. At such distances, solar heating remains far too weak to sublimate significant ice, so these objects must have formed dark or darkened through other processes. One explanation invokes space weathering by cosmic rays and solar wind particles that chemically alter surface ices and organics over millions of years, creating dark, reddish lag deposits. Laboratory experiments bombarding ice mixtures with energetic particles produce similar darkening, supporting this hypothesis. Alternatively, these objects may have formed from primordial material that was always dark, perhaps carbon-rich substances condensed from the outer regions of the protoplanetary disk, where temperatures remained so low that even volatile ices remained mixed with refractory organics. Such material would naturally be dark, reflecting little sunlight regardless of age or radiation exposure. Spectroscopic observations detect absorption features consistent with complex organic molecules, polycyclic aromatic hydrocarbons, tholins, and other carbon-based compounds that appear dark red to black. The discovery of objects like 47132521010VZ98 a Kuiper belt object with an extremely low geometric albedo, around 3%, demonstrates the population's diversity. This object's surface reflects sunlight even more poorly than fresh asphalt, making it one of the darkest known objects in the solar system. Its orbit and size suggest it's a typical Kuiper belt member, not an outlier, implying many similar dark objects await discovery. Current surveys, optimized for detecting brighter objects, systematically miss such dark targets, meaning the Kuiper belt's true population may be significantly underestimated. Statistical analysis of detected Kuiper belt object colors and albedos revealed bimodal distributions to distinct populations. One group shows moderate albedos around 12 to 15% with neutral to slightly red colors, interpreted as relatively pristine icy surfaces. The second group clusters around albedos below 6% with very red colors, interpreted as radiation-processed or compositionally distinct surfaces. The existence of two populations suggests different formation locations, different compositions, or different evolutionary pathways affected these objects over the solar system's history. Dark comets pose practical concerns for planetary defense. An object on a potentially hazardous orbit but too dark to detect with traditional surveys could approach Earth unnoticed until very close. While most dark comets remain in the outer solar system, gravitational perturbations occasionally send objects on paths that cross terrestrial planet orbits. Detecting such objects requires infrared surveys that can spot their thermal emission rather than relying on reflected sunlight. NASA's NEO-Surveyor mission, designed to detect asteroids using infrared observations, should also find dark comets, improving our census of these elusive objects. Gravitational anomalies detected by New Horizons. NASA's New Horizons spacecraft, after its historic Pluto flyby in 2015, continued into the Kuiper belt, flying past the contact binary object Arakoth in 2019. Throughout its journey, ground-based radio tracking monitored the spacecraft's trajectory with extraordinary precision, measuring its velocity to better than 1 millimeter per second. Analysis of this tracking data revealed tiny, unexplained accelerations, deviations from the path, predicted using only the Sun's and known planets' gravity. While small, these gravitational anomalies worry scientists because they suggest either unknown mass in the outer solar system or a breakdown in our understanding of gravity at the solar system's edge. The anomalies appeared as velocity changes of just fractions of a millimeter per second accumulated over years. Individual measurements showed scatter and noise, but statistical analysis revealed a persistent trend. New Horizons moved slightly faster or slower than expected, in ways that correlated with its position rather than random errors. Initial investigations ruled out systematics like gas leaks from the spacecraft's hydrazine thrusters or thermal radiation pressure from the spacecraft's radioisotope thermoelectric generator. The effect appeared genuinely external, something pulling on New Horizons from outside. One hypothesis attributes the anomalies to the Kuiper belt's gravitational field. Although individual Kuiper belt objects exert negligible force on the spacecraft, the collective gravity of billions of unseen objects could create a measurable acceleration. Computer models summing the expected gravitational contributions from known objects, plus statistical populations of undiscovered ones, generated accelerations comparable to observations. However, these models required assuming the Kuiper belt contains several times more mass than detected plausible but unconfirmed. An alternative explanation invokes modified Newtonian dynamics, MOND, a controversial theory proposing that gravity behaves differently when accelerations become extremely small. In MOND, the gravitational force doesn't decrease strictly as the inverse square of distance, but transitions to a different scaling law at very low accelerations. The theory was developed to explain galaxy rotation curves without invoking dark matter, but if correct, it should also affect spacecraft in the outer solar system where solar gravity weakens to comparable levels. MOND predicts a small anomalous acceleration directed toward the galactic center, roughly matching New Horizons observations in magnitude and direction. However, MOND remains highly controversial, contradicting relativity and lacking a viable theoretical foundation. The Pioneer anomaly provides historical context. NASA's Pioneer 10 and Pioneer 11 spacecraft, launched in the 1970s, also showed small, unexplained accelerations as they traveled to the outer solar system and beyond. Directed toward the Sun, the Pioneer anomaly persisted for decades, before eventually being explained as thermal radiation pressure, heat from the spacecraft's power source radiating asymmetrically, and creating a tiny but constant rocket effect. The resolution highlighted how difficult isolating true gravitational effects from spacecraft systematics can be. New Horizons designers learned from Pioneer and included better thermal modelling, but some uncertainty remains. Recent reanalysis of New Horizons tracking data, incorporating improved solar system ephemerides and updated asteroid and Kuiper belt object catalogues, reduced but didn't eliminate the anomalies. The residual acceleration, now estimated at a few millimeters per second squared, could result from several Earth masses distributed through the Kuiper belt beyond the spacecraft's trajectory. Alternatively, it could arise from systematic errors in tracking data analysis, subtle relativistic effects not perfectly modelled, or even unknown physics affecting radio signal propagation through the solar wind and interstellar medium. Upcoming missions will provide crucial tests. If the anomalies result from Kuiper belt mass, spacecraft on different trajectories should experience different accelerations depending on the unseen mass distribution. NASA is considering extended missions for New Horizons and potential future Kuiper belt or interstellar probes. These missions would carry improved instrumentation and more precise tracking capabilities, allowing detection of even smaller gravitational effects. Comparing multiple spacecraft trajectories will distinguish true gravitational anomalies from spacecraft-specific systematics, potentially revealing whether the outer solar system hides substantial unseen mass or whether our gravitational theories require refinement. The scattered disk's extreme eccentricities. Beyond the classical Kuiper belt lies the scattered disk, a region populated by objects on highly eccentric and inclined orbits that bring them alternately close to Neptune and far into the remote outer solar system. Objects like Eris, with an orbit ranging from 38 to 98 astronomical units, exemplify this population, but detailed orbital analysis revealed that scattered disk objects exhibit even more extreme eccentricities than Neptune's gravitational scattering alone should produce. Some objects reach perihelia near 30 astronomical units, but aphelia exceeding 500 astronomical units, requiring either additional perturbers or scattering events beyond Neptune's capability. These extreme eccentricities worry scientists because they imply the early solar system's dynamics were more violent and chaotic than standard planetary migration models describe. Standard models of Neptune's migration explain most scattered disk objects. As Neptune migrated outward from its formation location, it gravitationally scattered nearby planetesimals. Some were ejected from the solar system entirely, some fell inward toward the Sun, and others were placed on elongated orbits forming the scattered disk. Computer simulations of this process reproduce the observed distribution reasonably well, but underpredict the number of objects on the most eccentric orbits. Objects with perihelia just beyond Neptune, but aphelia exceeding 300 astronomical units, appear less commonly in simulations than in observations, suggesting an additional scattering mechanism. One explanation invokes a fifth giant planet that once orbited between Uranus and Neptune. Simulations show that such a planet could have undergone a dynamical instability, gravitationally interacting with the other giants and eventually being ejected from the solar system entirely. Before ejection, this planet would have scattered countless smaller objects onto highly eccentric orbits, populating the scattered disk's most extreme members. The NICE model of solar system evolution incorporates such an event, predicting that one ice giant was ejected early in the solar system's history. Evidence for this ejection includes the scattered disk's population structure and possible disturbances in the Kuiper belt. Another hypothesis suggests that close stellar encounters during the Sun's youth, when it resided in a dense star-forming cluster, perturbed objects onto extreme orbits. Passing stars would exert tidal forces on the outer solar system, lifting perihelia and scattering objects into distant orbits. This mechanism operates independent of Neptune's migration and would create a population of objects on orbits Neptune couldn't produce. Recent simulations of stellar cluster environments show that several close stellar passages are expected during the first 100 million years, sufficient to scatter numerous objects into the observed distributions. Observations of specific scattered disk objects provide clues. Eris, slightly smaller than Pluto, orbits with an eccentricity of 0.44, carrying it from 38 to 98 astronomical units. Its high inclination 44 degrees to the ecliptic suggests a violent scattering event, but Neptune alone can't easily generate such tilted orbits. The object 2013 SY99, with perihelion at 50 astronomical units and aphelion near 775 astronomical units, represents an even more extreme case. Its orbit suggests minimal interaction with Neptune, raising questions about how it arrived at such a configuration. The scattered disk's inclination distribution also puzzles researchers. While many scattered disk objects orbit near the ecliptic plane, a significant fraction have inclinations exceeding 20 degrees, with some approaching 90 degrees. Neptune's scattering primarily affects objects near the ecliptic, inefficiently tilting orbits to high inclinations. The observed inclination distribution requires additional mechanisms, perhaps the ejected planet hypothesis, stellar encounters, or even perturbations from the hypothetical planet 9 if it exists on a highly inclined orbit. Chemical and spectroscopic studies of scattered disk objects reveal compositions similar to classical Kuiper belt objects, surfaces dominated by water ice mixed with methane, nitrogen, and carbon-based compounds. This compositional similarity suggests scattered disk objects formed in the same region as classical Kuiper belt objects and were later dynamically scattered. However, subtle differences in volatile abundances hint at thermal processing or formation in slightly warmer regions closer to Neptune. As these objects scattered outward, they retained compositional signatures of their birthplaces, providing clues to the early solar system's temperature and density structure. Plasma density fluctuations in the outer heliosphere. The heliosphere's outer regions, where the solar wind slows and eventually terminates at the termination shock, exhibit plasma density fluctuations far more extreme than models predicted. Voyager spacecraft crossing the termination shock detected rapid variations in plasma density, changes of 50% or more occurring over hours to days. These plasma density fluctuations worry scientists because they indicate instabilities and turbulence in the solar wind's interaction with the interstellar medium, potentially affecting cosmic ray modulation and space weather forecasting for future deep space missions. The termination shock forms where the supersonic solar wind abruptly slows to subsonic speeds as it encounters back pressure from the interstellar medium. This shock should be relatively smooth according to simplest models, but Voyager 1's crossing at 94 astronomical units in 2004 revealed a far more complex structure. The spacecraft crossed and recrossed the shock multiple times over several months, indicating the shock boundary oscillated back and forth in response to solar wind pressure variations. Plasma density measurements showed fluctuations ranging from 0.002 to 0.005 particles per cubic centimetre, more than doubling within days. Voyager 2's termination shock crossing at 84 astronomical units in 2007 at a different location and time showed similar variability but with different characteristics. The shock appeared more abrupt, with fewer crossings, but plasma density continued fluctuating in the heliosheath beyond. These fluctuations didn't correlate, obviously, with solar wind conditions measured earlier at the spacecraft's previous locations, suggesting local processes in the heliosheath generated the variations, rather than simply reflecting solar wind variability propagating outward. Theoretical models attempting to explain these fluctuations invoke several mechanisms. Instances at the termination shock itself can generate waves that propagate through the heliosheath, alternately compressing and rarefying the plasma. Magnetic reconnection events, where solar and interstellar magnetic field lines merge and break, could create localized plasma density enhancements. Turbulence generated by the solar wind's interaction with the heliopause might cascade down to smaller scales, creating fluctuations on the timescales Voyager observed. Plasma wave measurements provided additional insights. Both Voyagers detected intense plasma oscillations near the termination shock and throughout the heliosheath. These waves, with frequencies ranging from hundreds of hertz to kilohertz, carry energy and momentum, potentially driving the observed density fluctuations. The waves appear generated by unstable particle distributions, particularly pickup ions, created when neutral atoms from the interstellar medium enter the heliosphere, become ionized, and are accelerated by the solar wind's magnetic field. These ions form ring-shaped distributions in velocity space that excite plasma waves through various instabilities. The discovery of magnetic field structures called flux ropes in Voyager data revealed another source of plasma variability. Flux ropes are twisted magnetic field lines forming rope-like structures that trap plasma and propagate through space. When Voyager encountered these structures, plasma density spiked, magnetic field strength increased, and sometimes field direction reversed briefly. Flux ropes likely form through magnetic reconnection and represent transient features carried by the solar wind into the heliosheath. Their irregular spacing and orientations create stochastic plasma density variations as they pass the spacecraft. Cosmic ray modulation by heliosheath plasma fluctuations adds practical importance. Cosmic rays entering the heliosphere diffuse through magnetic field irregularities, scattering as they propagate inward. The scattering efficiency depends on plasma density and turbulence levels denser. More turbulent plasma scatters cosmic rays more effectively. Fluctuations in heliosheath plasma thus modulate cosmic ray intensities reaching the inner solar system, affecting radiation exposure for astronauts and potentially influencing Earth's atmosphere through cosmic ray-induced ionization. The hydrogen wall's variable thickness. Just beyond the heliopause, where solar wind pressure balances interstellar pressure, neutral hydrogen atoms accumulate into a dense structure called the hydrogen wall. First predicted theoretically and later detected by IBEX observations, this wall forms because hydrogen atoms flowing in from interstellar space slow down when encountering the solar wind's outflow, piling up like cars slowing in traffic. But IBEX measurements revealed that the wall's thickness and density vary significantly, with direction thicker in some parts of the sky than others. This variable thickness worries scientists because it suggests asymmetries in either the solar wind or interstellar medium that current models don't fully capture. The hydrogen wall's existence results from a straightforward physical process. Neutral hydrogen atoms in the local interstellar medium move toward the solar system at roughly 25 kilometers per second. As they approach the heliopause, they encounter a region where the solar wind has slowed and compressed against interstellar pressure. This creates a zone of increased density where hydrogen atoms decelerate like a traffic jam forming when fast-moving cars encounter a slowdown. The accumulated hydrogen scatters ultraviolet light from distant stars, creating a faint glow that IBEX detects. IBEX measurements, spanning a full solar cycle, showed the wall's properties vary with both direction and time. In the direction the solar system moves through the interstellar medium, the nose direction, the wall appears thicker and brighter, consistent with more hydrogen piling up where the heliosphere plows most directly into interstellar material. But in perpendicular directions, the wall shows unexpected enhancements and deficits, suggesting the interstellar medium's density itself varies with direction, or that the heliopause's shape creates focusing effects. Temporal variations add another puzzle. The wall's brightness changed by approximately 15% over 7 years of observations, correlating loosely with solar activity. During solar maximum, when the solar wind strengthens, the heliopause pushes outward and the wall shifts to greater distances. During solar minimum, interstellar pressure dominates more and the wall moves inward. These shifts change the wall's density and thus its brightness. However, the observed variations exceeded those predicted by models incorporating only solar cycle effects, suggesting additional variability sources. One possibility involves structure in the local interstellar cloud surrounding the solar system. Voyager measurements indicated the interstellar medium's density averages around 0.08 particles per cubic centimeter, but small-scale density variations, cloudlets or filaments within the larger cloud could create localized enhancements. As the solar system moves through these structures, it encounters varying interstellar densities, changing the hydrogen wall's properties. The timescale for crossing a small cloudlet depends on its size and the solar system's speed, but could range from years to decades consistent with observed variations. Another hypothesis attributes variations to solar wind fluctuations at different solar latitudes. The solar wind's speed and density vary with latitude, faster and less dense at the poles and slower but denser near the equator. As the sun's magnetic field flips every 11 years, the pattern shifts, changing how the solar wind interacts with interstellar material in different directions. These latitude-dependent variations could create asymmetries in the hydrogen wall, making it thicker where slower, denser solar wind encounters interstellar hydrogen, and thinner where faster wind sweeps hydrogen away more efficiently. Spectroscopic observations of the wall's scattered ultraviolet light revealed another clue: the hydrogen's temperature. The wall's hydrogen appears warmer than the bulk interstellar medium, reaching temperatures around 10,000 Kelvin compared to 7,000 Kelvin farther out. This heating likely results from the deceleration process itself. Hydrogen atoms slowing down convert kinetic energy into thermal energy. But the temperature distribution shows asymmetries, warmer in some directions than others, hinting at varying interaction strengths around the heliosphere. Anomalous trajectories of long-period comets. Long-period comets arrive from the Oort cloud on nearly parabolic orbits, passing close to the Sun before returning to the outer solar system. Precise tracking of these comets occasionally reveals trajectory anomalies, deviations from pure gravitational paths that require non-gravitational forces to explain. While outgassing from sublimating ice accounts for most such anomalies, some comets show deviations inconsistent with standard outgassing models, suggesting either unusual outgassing patterns or additional perturbing influences. These anomalous trajectories worry scientists because understanding cometary motion matters for planetary defense, and unexplained deviations could indicate gaps in our knowledge of cometary physics or even undetected perturbers in the outer solar system. Non-gravitational forces arise when sublimating ice creates jets of gas and dust from a comet's surface. These jets act like small rocket engines, pushing the comet slightly off its purely gravitational path. The effect depends on the comet's rotation, active area distribution, and gas production rate parameters that vary widely between comets. Astrometric observations tracking comet positions over months or years reveal these tiny accelerations, typically measured in millionths of a meter per second squared. Some comets, however, show non-gravitational accelerations far larger or in unexpected directions compared to outgassing models. Comet C, 2010X1 Elenin, for example, exhibited acceleration components that couldn't be reconciled with any reasonable outgassing model. The comet disintegrated during perihelion passage, complicating analysis, but earlier trajectory anomalies suggested either highly asymmetric outgassing or an external perturbation. Similar anomalies appeared in other comets' orbits, raising questions about what processes drive such deviations. One explanation invokes outgassing from subsurface reservoirs. As a comet approaches the Sun, heat penetrates its crust, vaporizing buried ice pockets that erupt through weak points. These eruptions occur sporadically, creating intermittent, strong jets that accelerate the comet unpredictably. Without detailed knowledge of each comet's internal structure and composition, modeling such outbursts remains speculative, making trajectory predictions uncertain. Another possibility involves spin axis changes driven by outgassing torques. Asymmetric jets not only accelerate a comet's center of mass, but also apply torques that change its rotation. As the spin axis precesses, jet directions shift relative to the comet's orbital motion, creating complex acceleration patterns. Some comets show evidence of such spin changes, their light curves revealing period variations consistent with precession. Incorporating spin dynamics into trajectory models improves fits, but requires assumptions about comet shape and active region locations. More exotic explanations invoke external perturbers. A hypothetical Planet 9, if it exists, would gravitationally perturb comets passing through certain regions of the sky. These perturbations would appear as non-gravitational accelerations if Planet 9's mass and location aren't included in orbit calculations. Searching for such signals in long-period comet orbits could constrain or detect Planet 9 indirectly. However, distinguishing gravitational perturbations from outgassing effects requires precise astrometry and large comet samples, challenging given that long-period comets are faint and observed only briefly. Interstellar medium drag provides another potential force. Although extremely tenuous, the interstellar medium exerts drag on objects moving through it. Comets entering the heliosphere from the Oort cloud move relative to both the solar system and interstellar medium. Drag forces depend on the comet's size, velocity, and the medium's density, typically negligible for large comets, but potentially significant for small ones, or during passages through denser interstellar cloudlets. Calculating drag requires knowing interstellar density along the comet's path, information only now becoming available through Voyager measurements. Statistical analysis of long-period comet orbits revealed possible clustering in orbital elements. Some studies suggested comets arriving from certain directions share similar orbital characteristics more often than randomness predicts. If confirmed, such clustering could indicate past gravitational perturbations by a massive body, either Planet 9 or a passing star. However, other analyses found no significant clustering after accounting for observational biases, leaving the question unresolved. Trans-Neptunian binaries and unusual mass ratios. Surveys of trans-Neptunian objects revealed that many exist as binaries, two objects orbiting their common center of mass. Pluto and Charon form the most famous example, but hundreds of additional binaries populate the Kuiper belt. Analysis of these systems showed an unusual feature. Their mass ratios differ significantly from asteroid binaries in the inner solar system. Many trans-Neptunian binaries have near-equal mass components, while inner solar system binaries typically feature one dominant primary with a much smaller secondary. These unusual mass ratios worry scientists because they constrain formation mechanisms and may reveal dynamical processes unique to the early outer solar system. Binary formation in the Kuiper belt likely occurred through several mechanisms. Gentle collisions between similar-sized objects during the solar system's youth could have resulted in capture rather than disruption, leaving behind bound pairs. Gravitational interactions during close encounters, possibly assisted by dynamical friction from surrounding debris, might have enabled capture without physical contact. Alternatively, some binaries may have formed directly from the protoplanetary disk as separate condensations within a single collapsing cloud fragment. The equal mass preference suggests formation through collisions or three-body interactions. When two objects of similar size collide at low velocity, they can exchange enough momentum to become gravitationally bound if the impact isn't head-on. Computer simulations showed that such gentle collisions were more common in the early, more densely populated Kuiper belt. Objects on similar orbits approached each other at low relative velocities, increasing the likelihood of capture. As the Kuiper belt's population diminished over time through scattering and collisions, binary formation opportunities decreased, explaining why binaries appear more common among certain dynamical classes. Observations revealed that cold classical Kuiper belt objects, those on nearly circular low-inclination orbits, show much higher binary fractions than other populations. Estimates suggest that 20 to 40% of cold classical objects are binaries, compared to only a few percent among scattered disk or resonant objects. This disparity indicates cold classical objects experience different dynamical conditions, perhaps remaining undisturbed in their formation locations, while other populations underwent scattering that disrupted binaries. The orbits of trans-Neptunian binaries also differ from inner solar system counterparts. Many have wide separations, tens of thousands of kilometers, and low eccentricities. Such configurations are fragile. Close encounters with Neptune or other massive bodies would easily disrupt them. Their survival over 4.5 billion years implies minimal perturbations, supporting the idea that cold classical Kuiper belt objects remain dynamically cold since formation. The orbital properties thus encode information about the outer solar system's dynamical history. Spectroscopic observations of binary components revealed compositional similarities between partners, suggesting they formed together from the same material. However, some binaries show color or spectral differences, indicating either heterogeneous formation regions or subsequent evolutionary divergence. If components formed separately and were later captured, compositional differences might be expected. Conversely, if they formed together, similarities should dominate. Current data show mixed results, with some binaries matching closely and others differing, suggesting multiple formation pathways contributed to the observed population. The discovery of contact binaries like Arakoth New Horizons' 2019 flyby target provided a fascinating variant. Arakoth consists of two lobes gently joined at a narrow neck, resembling a snowman. This structure likely formed when two separate objects orbited each other, gradually spiraling inward through tidal friction and eventually touching. The gentle merger preserved delicate surface features and caused minimal disruption, indicating it occurred at extremely low velocity, less than a few meters per second. Such gentle mergers might represent an intermediate stage in binary evolution, with some systems remaining as separated binaries while others coalesced into contact binaries. Detection of unexpected dust lanes beyond Neptune. Interplanetary dust pervades the solar system, produced by asteroid collisions, comet outgassing, and collisions among Kuiper belt objects. Infrared observations from spacecraft like IRAS and Spitzer mapped dust distributions throughout the inner solar system, revealing zodiacal light patterns and debris rings. But recent observations from New Horizons' dust counter detected unexpected dust concentrations beyond Neptune regions where models predicted very low dust densities. These unexpected dust lanes worry scientists because they suggest either unmodeled dust sources or transport mechanisms that redistribute dust more efficiently than thought. The student dust counter aboard New Horizons measured impacts from tiny dust grains throughout the spacecraft's journey. In the inner solar system, impact rates match predictions based on zodiacal dust models. But beyond 30 astronomical units, instead of declining smoothly, impact rates showed oscillations, regions of higher and lower dust density alternating as the spacecraft travelled. These variations didn't correlate with known Kuiper belt object concentrations or obvious sources, suggesting dynamical processes concentrated dust into lanes or streams. One hypothesis attributes the lanes to mean motion resonances with Neptune. Just as asteroids cluster in orbital resonances with Jupiter, dust particles can become trapped in resonances with Neptune, creating concentrations at specific heliocentric distances. Computer simulations showed that dust produced by Kuiper belt collisions migrates inward through radiation pressure and gravitational perturbations. As particles drift, they spend more time in resonant regions where orbital periods match Neptune's in simple integer ratios. These resonant trappings create dust lanes detectable by passing spacecraft. Another possibility involves dust production rate variations over time. If Kuiper belt collisions occur sporadically, perhaps concentrated during periods when Neptune's migration perturbed orbits into crossing configurations, dust production would pulse. Dust released during different epochs would spread along orbital paths, creating shell-like structures. A spacecraft passing through these shells would detect alternating high and low dust densities corresponding to dust produced at different times. The spacing between shells would reflect the typical time between major collisional events and the dust particles' drift rates. Spectroscopic analysis of dust grain compositions, inferred from their impact velocities and directionality, suggested they originated from Kuiper belt collisions rather than cometary outgassing. The grains' high impact speeds indicated they were on eccentric orbits, consistent with debris from collisional cascades among Kuiper belt objects. If correct, the dust lanes map the debris trails from ongoing collisional evolution, revealing where Kuiper belt collisions are most active. Unexpectedly, some dust impacts measured by New Horizons showed velocities suggesting interstellar origin. These grains approached from directions aligned with the interstellar medium's flow direction and moved at speeds exceeding solar escape velocity. Their detection confirmed that interstellar dust penetrates deep into the solar system, reaching at least the Kuiper belt. The flux of interstellar dust appears higher than pre-mission predictions, suggesting either local interstellar density enhancements or that interstellar grains penetrate the heliosphere more easily than models predicted. The dust lane discoveries have implications for future missions. Spacecraft venturing into the Kuiper belt will encounter variable dust environments, with some regions posing higher impact hazards than others. Understanding dust distributions helps mission planners design shielding and choose trajectories minimizing risk. Additionally, dust dynamics constrain Kuiper belt mass and collisional activity parameters, essential for understanding solar system formation and evolution. The detached object population and orbital extremes. Beyond the scattered disk lies an even more mysterious population, detached objects. These bodies have perihelia too distant for Neptune to have placed them directly, typically beyond 50 astronomical units, yet they orbit the Sun on bound paths. Objects like Sedna, with a perihelion of 76 astronomical units, and Liliuohonua, discovered recently with similar orbital characteristics, cannot have been scattered by Neptune alone. Their existence worries scientists because explaining their origins requires invoking processes beyond standard planetary migration, possibly including stellar encounters, rogue planets, or an undiscovered massive planet in the outer solar system. Detached objects occupy a peculiar dynamical niche. Unlike scattered disk objects, which have perihelia close enough for Neptune to occasionally perturb them, detached objects never approach Neptune. Their aphelia reach hundreds to nearly 1,000 astronomical units, placing them among the most distant known solar system objects during large portions of their orbits. This isolation means they've remained dynamically undisturbed since being placed in their current orbits, preserving clues about whatever process created them. Sedna exemplifies the population. Discovered in 2003, it orbits the Sun every 11,000 years, on a path ranging from 76 to approximately 936 astronomical units. Spectroscopic observations revealed a reddish surface suggesting organic compounds similar to other outer solar system bodies, but Sedna's orbit remains unexplained by standard models. Neptune's gravity can't lift perihelia to 76 astronomical units, and no known mechanism naturally produces such orbits during solar system formation. The discovery of additional detached objects like 2012 VP113 strengthened the mystery. With a perihelion at 80 astronomical units, even more detached than Sedna, VP113 suggested a whole population of similar bodies. Statistical analysis indicated that if a complete census were possible, dozens to hundreds of detached objects might exist, each recording the same mysterious formation process. Their orbital elements showed tentative clustering, hinting that a common perturber shaped their paths. One explanation invokes the early solar system's stellar environment. The Sun formed in a dense star cluster where encounters with other stars occurred frequently. A passing star approaching within a few hundred astronomical units could gravitationally perturb objects in the outer solar system, lifting perihelia of some into detached orbits. Computer simulations showed that one or two close stellar encounters during the Sun's first 100 million years could produce the observed detached population. This hypothesis predicts that other stars should also harbour detached object populations, potentially observable as planets are discovered around nearby stars. The Planet 9 hypothesis offers another explanation. A massive planet on a distant, eccentric orbit would gravitationally shepherd objects, some being scattered into detached orbits during close approaches. Simulations, incorporating a 5 to 10 Earth-mass planet between 400 and 800 astronomical units, reproduced the observed clustering and detachment of known objects' orbits. The planet's gravity would also explain perpendicular and retrograde objects, adding consistency to the hypothesis. More exotic proposals include a captured rogue planet or brown dwarf currently orbiting in the outer solar system. Such an object, if massive enough and on the right orbit, could produce the observed perturbations. However, infrared surveys like WISE have ruled out brown dwarf mass objects within 10,000 astronomical units, constraining this hypothesis unless the object is smaller and farther than current detection limits. Recent discoveries continue adding to the detached population. Objects like 2015 TG387, nicknamed the Goblin, with perihelion at 65 astronomical units, and 2018 VG18, Far Out, reinforced that the population is real and significant. Each new discovery refines orbital statistics, helping discriminate between formation hypotheses. Clustering analyses remain contentious, with some studies finding significant alignment and others attributing it to observational bias. But the debate drives more comprehensive surveys, high-energy particle acceleration regions. Throughout the solar system, regions exist where charged particles accelerate to extremely high energies through various processes. Near Earth, magnetic reconnection and shock waves accelerate electrons and ions to relativistic speeds. At Jupiter, the powerful magnetic field and rapid rotation create the solar system's most intense radiation belts. But observations from Voyager, New Horizons, and other spacecraft revealed high-energy particle acceleration occurring in unexpected locations deep in the outer heliosphere, at the termination shock, and even beyond the heliopause. These high-energy particle acceleration regions worry scientists because they indicate unknown acceleration mechanisms and pose radiation hazards to spacecraft exploring those regions. The termination shock, where the solar wind abruptly slows from supersonic to subsonic speeds, functions as a particle accelerator. Voyager spacecraft crossing this boundary detected sudden increases in energetic ions and electrons, some accelerated to million electron-volt energies. The acceleration results from shock drift acceleration particles bouncing back and forth across the shock front, gain energy with each crossing, progressively accelerating to higher velocities. Computer simulations showed this process can accelerate particles to cosmic ray energies given sufficient time and favourable magnetic field configurations. But unexpectedly, both Voyagers also detected energetic particle increases at the heliopause itself. Despite the heliopause not being a traditional shock, plasma doesn't flow supersonically there. The sharp change in plasma and magnetic field properties creates conditions for particle acceleration. Magnetic reconnection at the boundary where solar and interstellar fields meet releases energy, accelerating nearby particles. Additionally, turbulence and magnetic field fluctuations scatter particles, enabling diffusive shock acceleration even without a well-defined shock front. New Horizons instruments detected sporadic bursts of energetic particles during its traverse of the Kuiper belt far from known acceleration sites. These events, lasting hours to days, showed particle energy spectra consistent with local acceleration rather than particles transported from closer to the sunday. The source remains unclear, but possibilities include magnetic reconnection events in the solar wind, interactions between the solar wind and local interplanetary magnetic field structures, or even particle acceleration by shock waves from distant solar eruptions propagating through the outer heliosphere. Comparison of particle acceleration at different locations revealed common features. All acceleration sites show enhanced magnetic field turbulence, suggesting waves play crucial roles in energizing particles. Plasma wave measurements from Voyager and other missions detected intense oscillations near acceleration regions, electromagnetic and electrostatic waves with frequencies ranging from fractions of hertz to kilohertz. These waves can resonantly interact with particles, transferring energy and accelerating them through various wave-particle interaction mechanisms. The connection between solar activity and outer heliosphere particle acceleration adds complexity. During solar maximum, the Sun emits more coronal mass ejections and drives stronger shock waves into the heliosphere. These shocks propagate outward, reaching the termination shock and beyond. When they arrive, they trigger additional particle acceleration, temporarily boosting energetic particle fluxes. Voyager observations showed such events, with particle intensities increasing days to weeks after solar eruptions, the time required for disturbances to propagate to the spacecraft's location. Unexpectedly high fluxes of anomalous cosmic rays particles, originating as neutral atoms from the interstellar medium that become ionized in the heliosphere and then accelerated, raised questions about where and how efficiently acceleration occurs. Initially thought to be accelerated primarily at the termination shock, some anomalous cosmic rays appeared accelerated farther out, possibly in the heliosheath or at the heliopause. Understanding their acceleration sites and mechanisms helps model how galactic cosmic rays propagate through the heliosphere and how the solar system interacts with its interstellar environment. The solar wind's asymmetric termination and sectored structure. The solar wind, a continuous stream of charged particles flowing outward from the Sun at speeds ranging from 300 to 800 kilometers per second, was long assumed to terminate uniformly at the termination shock in all directions, but measurements from both Voyager spacecraft revealed profound asymmetries in where and how the solar wind terminates. Voyager 1 crossed the termination shock at 94 astronomical units in the direction of the Sun's motion through the galaxy, while Voyager 2 encountered it at only 84 astronomical units, a difference of 10 astronomical units, or approximately 1.5 billion kilometers. This asymmetric termination worries scientists because it indicates the heliosphere's shape differs dramatically from simple models and suggests the interstellar medium applies varying pressure on different sides of the solar end system. The asymmetry results from the Sun's motion through the local interstellar medium at approximately 26 kilometers per second. Like a ship moving through water, the heliosphere experiences ram pressure on its leading edge, the nose direction, where it plows into oncoming interstellar material. This compression pushes the termination shock closer to the Sun in that direction. On the trailing side, the tail, the heliosphere stretches out like a windsock, extending the termination shock to greater distances and possibly forming an elongated heliotail, extending hundreds of astronomical units downstream. But the 10 astronomical unit difference between Voyager crossings exceeds what simple ram pressure models predict. The discrepancy suggests additional factors shape the heliosphere beyond just the Sun's motion. The interstellar magnetic field, oriented roughly perpendicular to the Sun's velocity vector, exerts magnetic pressure that preferentially compresses certain regions while allowing others to expand. Computer simulations incorporating realistic interstellar magnetic field strengths and orientations reproduce the observed asymmetry, showing the field creates a croissant or kidney bean-shaped heliosphere, rather than a symmetric bullet or teardrop. Within the heliosphere itself, measurements revealed sectored structure in the solar wind regions of opposite magnetic field polarity, separated by current sheets. These sectors originate from the Sun's rotating magnetic field, which organizes into a pattern resembling a ballerina's twirling skirt. As the Sun rotates, this structure sweeps past Earth and other planets, creating alternating sectors of toward and away magnetic field polarity. The sectors persist into the outer heliosphere, affecting how the solar wind interacts with the termination shock and potentially creating longitudinal variations in shock properties. Voyager observations showed that the termination shock strength varies with position. Voyager 2 encountered a stronger shock than Voyager 1, with plasma compression ratios and temperature increases differing by approximately 20 to 30%. These variations likely result from the solar wind's sectored structure and time-variable nature. The Sun's 11-year activity cycle modulates solar wind properties, and the decades-long journey to the termination shock means each Voyager encountered shock conditions driven by different solar activity levels. Disentangling spatial variations from temporal changes challenges researchers attempting to construct comprehensive heliosphere models. Temperature measurements in the heliosheath, the region between the termination shock and heliopause, revealed unexpected thermal structure. Instead of uniformly hot plasma, the Voyagers detected regions of varying temperature, with some zones exceeding 100,000 Kelvin, while others remained cooler. These temperature variations correlate with plasma density fluctuations and magnetic field changes, suggesting the heliosheath is thermally stratified. The heating mechanisms likely include compression and shock processing of solar wind plasma, but magnetic reconnection and wave-particle interactions may also contribute. The discovery of a hydrogen deflection region, where interstellar neutral hydrogen flowing into the solar system gets deflected by charge exchange interactions, added another layer of complexity. Neutral hydrogen atoms entering the heliosphere can capture electrons from solar wind ions, becoming newly ionized pickup ions, while the original solar wind ions become neutral and cease responding to magnetic fields. This charge exchange process creates a complex pattern of plasma and neutral flows that varies with position around the heliosphere. Models suggest the deflection creates asymmetries in both the solar wind's momentum distribution and the interstellar neutral atom flow pattern observed by spacecraft like IBEX. The sectored structure extends to energetic particle distributions as well. Voyager instruments detected that cosmic rays' high-energy particles from galactic sources penetrate the heliosphere more easily through certain sectors than others. The sectors with weaker magnetic field strength or more turbulent conditions allow cosmic rays to diffuse inward more rapidly. This preferential entry creates modulation patterns in cosmic ray intensities measured at Earth that correlate with solar rotation and the orientation of the Sun's global magnetic field. Understanding these patterns helps predict space radiation environments for crewed missions and potentially even influences on Earth's atmosphere. Recent measurements from IBEX and other missions mapping the heliosphere's global structure confirmed predictions of a heliotail extending asymmetrically from the solar system's trailing edge. This tail, shaped by the interplay between solar wind pressure and interstellar magnetic field draping, may extend hundreds of astronomical units and possibly exhibits instabilities that cause it to flap or even break apart periodically. No spacecraft has yet ventured into the heliotail to measure its properties directly, but remote sensing using energetic neutral atoms reveals its approximate shape and dynamics. The tail represents the final transition zone, where solar influence gives way to purely interstellar conditions, a frontier that future missions may explore. Gravitational focusing of interstellar material. As the solar system moves through the galaxy, it encounters interstellar gas and dust particles that flow past like cosmic wind. But these particles don't simply stream by uniformly. The Sun's gravity bends their trajectories, focusing them into enhanced density regions downwind of the Sunday. This gravitational focusing creates a focusing cone, where interstellar material accumulates at higher concentrations than the ambient interstellar medium. Observations from spacecraft instruments and detailed modeling reveal that this focusing affects not just neutral atoms but also dust particles, creating variability in interstellar material densities throughout the outer solar system. This gravitational focusing worries scientists because it means the interstellar environment within the heliosphere varies with position and time, potentially affecting spacecraft trajectories, dust impact rates, and even the heliosphere's overall structure. The focusing mechanism operates through classical gravitational dynamics. Neutral atoms and dust particles from the interstellar medium approach the solar system with velocities around 20 to 30 kilometers per second, fast enough that most pass through without being captured, but slow enough that solar gravity significantly deflects their paths. Particles passing closer to the Sun experience stronger deflection than those passing farther away. The geometry creates a caustic, a region of enhanced density on the downwind side of the Sun, where deflected trajectories converge. Measurements of interstellar helium by instruments aboard Ulysses, IBEX, and other missions confirmed the focusing cone's existence and properties. Peak densities in the cone exceed the ambient interstellar helium density by factors of 2 to 3, with the enhancement concentrated in a relatively narrow angular region, approximately opposite the direction of the interstellar wind. The cone's exact location and intensity vary with the incoming particle's velocity distribution and the Sun's gravitational field strength parameters that remain constant for any given particle species but differ between helium, hydrogen, oxygen, and heavier elements. Interstellar dust particles experience even stronger focusing effects because they're more massive and move more slowly than gas atoms. Observations from spacecraft dust detectors, including instruments on Ulysses, Galileo, and Cassini, detected interstellar dust flowing through the solar system from the direction of the local interstellar cloud. But impact rates varied systematically with the spacecraft's position, showing enhancements consistent with gravitational focusing predictions. The focusing creates dust density variations of factors of 5 to 10, significantly exceeding gas focusing effects. However, dust focusing is complicated by electromagnetic forces. Interstellar dust grains typically carry electric charges acquired through interactions with cosmic rays and ultraviolet starlight. As charged particles move through the interstellar magnetic field threading the heliosphere, they experience Lorentz forces that deflect their trajectories perpendicular to both their velocity and the magnetic field. For smaller grains with high charge-to-mass ratios, electromagnetic deflection can exceed gravitational effects, reducing or even eliminating focusing. Only larger grains, with diameters exceeding approximately 1/10 of a micrometer, experience gravitational focusing stronger than electromagnetic deflection. The time variability of focusing patterns adds another dimension. As the Sun moves through inhomogeneous interstellar medium regions with varying density, temperature, and velocity, the properties of inflowing material change over timescales of years to decades. Observations spanning multiple decades revealed gradual shifts in the interstellar helium flow direction and temperature, indicating the Sun has crossed between regions with subtly different properties. These variations alter the focusing cone's location and intensity, creating temporal changes in interstellar material densities throughout the heliosphere. Spectroscopic analysis of particles within the focusing cone revealed compositional information about the local interstellar medium. Instruments capable of measuring isotopic ratios detected variations in helium, 3 to helium, 4 ratios, oxygen isotopes, and other traces that constrain the interstellar medium's nucleosynthetic history. The measurements showed the local cloud surrounding the solar system has chemical properties intermediate between typical interstellar medium and material enriched by nearby supernova explosions, suggesting the Sun currently resides in a transition zone between different interstellar environments. Gravitational focusing of interstellar neutral particles creates secondary effects on the heliosphere itself. The enhanced densities in the focusing cone increase the rate at which neutral atoms undergo charge exchange with solar wind ions, creating additional pickup ions preferentially in that direction. These pickup ions add mass and momentum to the solar wind, subtly altering its flow pattern and potentially contributing to heliospheric asymmetries. Models incorporating this feedback showed modest but measurable effects on the termination shock's shape and the heliopause's position, demonstrating that gravitational focusing influences the solar system's interaction with its galactic environment. The discovery of temporal variations in interstellar dust impact rates on spacecraft correlated with predictions of how the focusing cone's properties should change as the Sun moves through structured interstellar medium. During periods when the interstellar wind shifted direction or slowed, the focusing cone relocated and weakened, reducing dust concentrations in regions it previously enhanced. These variations, measured over years of spacecraft operations, provided direct evidence that the Sun navigates through a dynamic, structured interstellar environment rather than uniform cosmic emptiness. The Kuiper cliff and the outer solar system's sharp edge. One of the most perplexing features discovered in the Kuiper belt is the Kuiper cliff, a sharp drop-off in object density beyond approximately 48 to 50 astronomical units from the Sunday. Surveys detecting thousands of Kuiper belt objects found that their numbers declined precipitously past this distance, falling by a factor of 10 or more within just a few astronomical units. This sharp edge worries scientists because standard models of solar system formation predict the protoplanetary disk extended far beyond 50 astronomical units. And while Neptune's migration cleared material from certain regions, no known mechanism cleanly truncates the belt at such a specific distance. The cliff's existence suggests either a dramatic event in the early solar system or an ongoing process that continues removing objects from the outer Kuiper belt. Early surveys in the late 1990s and early 2000s first detected hints of the cliff. As telescopes systematically scanned regions at increasing distances, the detection rate of Kuiper belt objects remained roughly constant out to about 45 astronomical units, then dropped sharply. Initially, astronomers suspected observational bias, perhaps objects at greater distances were simply too faint to detect with available instruments. But deeper surveys with larger telescopes confirmed the drop-off was real. Even accounting for the expected decrease in object brightness with distance, the number density truly declined beyond the cliff. Attempts to explain the cliff focused on dynamical mechanisms that could selectively remove objects from specific distance ranges. One hypothesis invoked the outward migration of Neptune during the solar system's first billion years. As Neptune migrated from roughly 20 to 30 astronomical units, it swept through the primordial Kuiper belt, scattering most objects it encountered. Objects interior to Neptune's final orbit were scattered inward or outward, while those beyond remained relatively undisturbed. But Neptune's migration alone doesn't explain a sharp edge. It should create a more gradual decline in density. Another explanation proposed that the protoplanetary disk itself had a sharp outer edge during the planet formation epoch. If the disk's surface density dropped abruptly beyond a certain radius, fewer planetesimals would have formed there, naturally creating a cliff in the present-day population. Theoretical models of disk formation show that sharp edges can arise if the disk viscosity or temperature structure changes rapidly at specific radii, perhaps due to phase transitions in ice chemistry or changes in turbulence properties. However, such sharp edges remain difficult to justify from first principles. The passing star hypothesis suggests that a close encounter with another star during the Sun's youth gravitationally truncated the Kuiper belt's outer edge. Simulations showed that a solar mass star passing within about 100 astronomical units could strip objects from the outer Kuiper belt through tidal forces, creating an abrupt edge. The encounter would have occurred during the Sun's time in its birth cluster, when stellar encounters were far more common than in the galaxy's current sparse environment. This hypothesis predicts other stars should also show truncated debris disks if they experience similar encounters, an observation that exoplanet surveys are beginning to test. Recent attention has focused on the Planet 9 hypothesis as a potential cliff explanation. A massive planet orbiting between 400 and 800 astronomical units would have shepherded nearby Kuiper belt objects through resonant interactions and close encounters. Simulations incorporating such a planet showed it could create a depletion zone in the outer Kuiper belt by ejecting objects or scattering them into the inner solar system. The planet's gravitational influence would extend inward to approximately 40 to 60 astronomical units through its strongest orbital resonances, potentially explaining the observed cliff location. Observations of the cliff's detailed structure revealed it's not perfectly sharp but shows some structure. Certain dynamical classes of objects, particularly those in mean motion resonances with Neptune such as the Plutinos, objects in 3:2 resonance, extend slightly beyond the general cliff location. This suggests that resonant protection allows some objects to survive at distances where non-resonant objects have been removed, a clue that dynamical sculpting rather than a primordial disk edge created the feature. Spectroscopic surveys comparing objects near the cliff with those at smaller distances revealed no obvious compositional differences. Objects on both sides of the cliff show similar colours, albedos, and spectral features, indicating they formed from the same material reservoir and experienced similar evolutionary processes. This compositional uniformity argues against models where the cliff marks a boundary between different formation environments and supports scenarios where dynamical processes selectively remove objects regardless of their composition. The total mass deficit implied by the cliff, comparing the observed population with extrapolations from the inner Kuiper belt, amounts to several Earth masses of material missing from the outer regions. This missing mass either was never there, was ejected from the solar system entirely, or resides in currently undetected reservoirs, such as very dark objects or materials scattered into the Oort cloud. Each possibility has different implications for solar system formation models and the efficiency of planetary migration in redistributing primordial material. Anomalous cosmic ray suppression zones. Cosmic rays, high-energy particles accelerated by supernovae, pulsars, and other violent astrophysical processes permeate the galaxy and continuously bombard the solar system from all directions. The heliosphere partially shields the inner solar system from these particles, with the solar wind and heliospheric magnetic field deflecting and scattering cosmic rays. But measurements from Voyager spacecraft and other missions revealed unexpected suppression zones, regions where cosmic ray intensities drop below expected levels even after accounting for known modulation processes. These anomalous cosmic ray suppression zones worry scientists because they suggest either gaps in understanding heliospheric shielding or the existence of localized magnetic structures that trap or deflect cosmic rays in ways current models don't predict. Cosmic ray modulation by the heliosphere follows well-established principles. As galactic cosmic rays diffuse inward from interstellar space, they scatter off magnetic field irregularities in the solar wind and heliosheath. This scattering reduces their ability to penetrate deeply, with the effectiveness depending on the particle's energies. Lower energy particles scatter more readily. Additionally, the Sun's 11-year magnetic activity cycle modulates cosmic ray intensities, with fluxes highest during solar minimum when the solar wind is weakest and lowest, during solar maximum when enhanced solar activity strengthens heliospheric shielding. Voyager 1's measurements after crossing the heliopause in 2012 showed the expected dramatic increase in cosmic ray intensity, roughly doubling for certain energy ranges, confirming it had exited the heliosphere's protective bubble. But unexpectedly, some energy ranges showed smaller increases than predicted, and certain particle species remained suppressed relative to expectations based on local interstellar spectra measured by other techniques. These discrepancies indicated that either the local interstellar medium's cosmic ray spectrum differs from assumptions, or some shielding mechanism persists even beyond the heliopause. One explanation invoked the depletion region just outside the heliopause, where cosmic rays remain partially excluded. Theoretical models predicted that magnetic field turbulence in the interstellar medium immediately surrounding the heliosphere continues scattering cosmic rays, creating a transition zone, tens of astronomical units thick, where intensities gradually rise toward true interstellar values. Voyager 1's measurements, taken just beyond the heliopause, might still be within this transition zone, explaining the incomplete cosmic ray recovery. Inside the heliosphere, Voyager 2 and other spacecraft detected localized suppression zones where cosmic ray intensities dropped by 10 to 30% over timescales of weeks to months. These events, called forbush, decreases when associated with solar activity, sometimes occurred without obvious solar triggers, suggesting internal heliospheric processes created them. Magnetic field measurements during these events revealed transient structures, possibly flux ropes or magnetic clouds, whose enhanced magnetic fields more effectively excluded cosmic rays from their interiors. The discovery of persistent cosmic ray gradients across the heliosphere revealed large-scale structure and shielding effectiveness. Spacecraft at different heliocentric distances but similar heliographic latitudes measured systematically different cosmic ray intensities, even after accounting for radial distance effects. The gradients correlated with the solar wind's sectored structure and with the tilt of the heliospheric current sheet, the warped surface separating oppositely directed magnetic field regions. Cosmic rays appeared to preferentially enter the heliosphere through regions where the current sheet intersected the heliopause, creating longitudinal variations in intensity. Measurements during solar minimum periods revealed unexpected cosmic ray suppression at Earth despite weak solar activity. Analysis showed this suppression correlated with enhanced interplanetary magnetic field strength, not from solar sources but from compression of the field by structures in the solar wind. Dense plasma regions, even without strong magnetic fields themselves, compressed the ambient interplanetary field, increasing its ability to scatter cosmic rays. This compression-enhanced shielding operated independently of solar activity and created variable cosmic ray environments depending on solar wind properties. Anomalous cosmic rays, particles originating as interstellar neutral atoms that become ionized and accelerated within the heliosphere, showed particularly puzzling suppression patterns. These particles, with energies between roughly 5 and 50 million electron volts, should populate the heliosheath abundantly since that's where most acceleration occurs. But Voyager measurements in the heliosheath detected anomalous cosmic ray intensities far below predictions, suggesting either acceleration mechanisms were less efficient than thought or transport processes preferentially removed these particles before they could accumulate. The suppression implied energy-dependent cosmic ray transport that models hadn't fully captured. The connection between cosmic ray variations and space weather has practical importance. Cosmic rays ionize Earth's atmosphere, affecting chemistry, cloud formation processes, and even climate on long timescales. Suppression zones that reduce cosmic ray fluxes reaching Earth could influence these processes, potentially affecting everything from atmospheric electrical properties to the formation of certain cloud types. Understanding what creates suppression zones helps predict cosmic ray variations and their terrestrial effects.